Here are two investments: a risky stock with 20% volatility and a safe bond at 8%. Mix them 50-50, and surely the risk is about 14%, the average. But it isn't. The actual risk is closer to 12. Risk doesn't average. It has a shape, and that shape is controlled by one number: correlation. This is the math of Markowitz and the geometry behind every modern portfolio. To reason about any portfolio, we need just two numbers: how much you expect to earn on average and how much that return could vary. Risk and reward. Every portfolio lives somewhere on this plane. A risky stock, asset A, sits up here. High return, high risk. A safe bond, asset B, sits down there. Low return, low risk. And an alternative, asset C, somewhere in between. Now mix them together. The expected return of the portfolio is a simple weighted average: 50% A, 30% B, 20% C. Expected return: 6% from A, 1.5 from B, 1.6 from C, 9.1%. The portfolio sits right there. Here's the key insight: expected return is easy, just a weighted average, always, linear, predictable. But risk? Risk is where the magic happens. But risk is different. You cannot just average the volatilities. The variance of the portfolio is a quadratic form: W transpose sigma W. Sigma is the covariance matrix. The diagonal holds the variances of each asset. The off-diagonal entries hold the covariances. And it's that covariance term that creates all the magic. Positive, zero, or negative, each one reshapes the portfolio's risk. Positive covariance, two assets moving together, amplifies risk. Negative covariance, they move apart, can actually cancel it out. That's diversification in a single formula. So what shape does this make in our risk-return plane? Back to just two of our three assets: the stock, asset A, and the bond, asset B. Section 2 told us that a portfolio's variance depends on one number hidden inside the covariance matrix. That number is the correlation, RO. Let's turn it like a dial and watch what happens to every possible mix of these two assets. When ρ equals +1, the two assets move in perfect lockstep. Mixing them gives you no diversification at all, just a straight line between the 2 points, averaging exactly as intuition predicts. Now turn the dial down. As correlation drops, the line starts to bow to the left. Every mix of the two assets is now a little less risky than the straight line average would suggest. At zero correlation, the assets are statistically independent. The curve bows further. Keep turning the dial past zero into negative territory. Negative correlation means when one asset zigs, the other tends to zag. When the stock falls, the bond tends to rise. At -1, perfect anti-correlation, something remarkable happens. The curve bends all the way to the y-axis itself. Zero risk. From two risky assets, not by chance, not by luck, by construction, at a guaranteed return of 7%, exactly between the stock's 12 and the bond's 5. But you don't get to choose correlation. The market picks it. Real bonds and real stocks sit somewhere between 0 and 1, never at -1. So, what happens when we stop picking just two assets and let a third one into the mix? Section 3 showed us that two assets trace out a curve, but a real portfolio can hold more. Here are our three: the stock A, the bond B, and the alternative C. What if we could mix all three in any proportion we like? Where do all those portfolios live? Let's find out. I'll sample 2,000 random weight vectors, each one a valid portfolio of our three assets, and I'll plot every one of them in the risk-return plane. Watch what happens. The cloud fills in a bullet-shaped region. Every mix you could ever construct lives inside this shape. Markowitz's bullet, the feasible region of this three-asset universe. The brighter dots have a higher Sharpe ratio, more return per unit of risk. But look closely at the edge, the upper left boundary of the cloud. It's not random at all. It's a curve, the efficient frontier. This leftmost point is the global minimum variance portfolio, the single lowest risk mix possible. For our three assets, it sits at roughly 7.3% risk and 5.3% expected return. The curve itself is a hyperbola in the risk-return plane. The exact solution comes from a single quadratic equation in the weights. But only half of this curve matters. The upper half above the GMVP is efficient. Every portfolio on it gives you the highest possible return for its level of risk. The lower half, below the GMVP, is dominated. Same risk, lower return. No rational investor ever picks these. One caveat: Our GMVP needs a small short position in the stock. We're allowing that for analytical cleanliness. Real portfolios often aren't. So here we are, a whole efficient curve of undominated portfolios, each one optimal for its own level of risk. But which one is the single best portfolio of them all? Section 4 left us with a curve of infinite efficient portfolios. Now let's add one more asset to the picture. A risk-free bond paying 3%, zero risk, guaranteed return. It sits right on the y-axis. Now something strange becomes possible. You can take any fraction of your money and put it in the risk-free bond, and the rest in some risky portfolio. The result traces a straight line on the risk-return plane, starting from the risk-free point. The slope of that line has a name, the Sharpe ratio. Expected excess return divided by risk, more return per unit of risk, higher slope, better portfolio. So the question becomes, how steep can we make that line? Watch. We'll rotate the line upward, making it steeper and steeper, too shallow, and the line cuts through the frontier. There are portfolios above it doing better, steeper, closer now. And at a slope of exactly 0.4844, the line just kisses the frontier at a single point. Any steeper, and the line no longer touches any portfolio. It's unreachable. This is the capital market line, the unique best linear trade-off between risk and return anywhere in the universe of our three assets. This tangency point is the single most efficient risky portfolio in existence for these three assets at this risk-free rate. It sits at about 11% risk, 8.4% expected return. The composition, 38% stock, 39% bond, 23% alternative. Every rational investor, given these inputs, should hold exactly this mix of risky assets. And here's the punchline. Every single efficient portfolio, every point on this line, is just a mix of two things, the risk-free bond and the tangency portfolio. Want less risk? Hold more of the bond. Want more? Borrow at the risk-free rate and hold more than 100% in the tangency mix. That's leverage. This is Tobin's two-fund separation theorem, 1958. Two funds are all you need. The capital market line answers how to build the best portfolio. But it doesn't tell us why the stock earns more than the bond in the first place. For that, we need one more idea. Here's the oldest question in finance. Why does Apple stock earn more than a Treasury bond? Apple returns around 12% a year, on average. A Treasury bond pays about 3%. One letter of the Greek alphabet answers that question. Beta, defined as the covariance of an asset's return with the market, divided by the market's variance. Intuitively, beta measures how much an asset moves when the market moves. For our three assets, beta of the stock is 1.68. It amplifies the market's swings. Beta of the bond is 0.37. It dampens them. Beta of the alternative sits near 1, moving roughly in lockstep with the market. Now a critical distinction. The capital market line lives in risk-return space, sigma on the x-axis. But there's a twin. The security market line uses beta instead. Same equilibrium, different view. And every one of our three assets, stock, bond, alternative, sits exactly on the SML. But never confuse them. The CML holds only for efficient portfolios. The SML holds for every asset. Different x-axis, different meaning. Here's why beta matters. The total risk of any asset splits into two parts. Systematic risk, beta squared times market variance, the part you can't escape, and idiosyncratic risk, everything else, the asset's individual story. The stock is 86% systematic, the bond only 27%. Diversification kills idiosyncratic risk. It cannot kill systematic risk. And this gives us the full CAPM equation. Expected return of any asset equals the risk-free rate plus beta times the market risk premium. Sharpe earned the 1990 Nobel Prize for this single line, building on Lintner's and Mawson's independent formulations. But here's where things get interesting. The covariance matrix that built all of this, it also builds something completely unrelated. Here's something remarkable. The covariance matrix sigma that built our entire portfolio theory has a twin, a much, much bigger one, living in a completely different world. Both matrices are symmetric. Both are positive semi-definite. The diagonal holds variances, which can never be negative. And that's enough. The spectral theorem applies. Any symmetric matrix can be diagonalized, written as an orthogonal matrix times a diagonal matrix times that orthogonal matrix transposed. Same proof, same eigenvectors, same eigenvalues. The sizes differ. One is 3 by 3, the other is tens of thousands. But the mathematics is identical. On the finance side, the first eigenvector of sigma tells us the market factor. Look at the loadings. All three assets load on it with the same sign, all positive. 71% of all the risk in our three-asset universe sits on this single direction. When this one factor moves, everything moves together. This is why real equity markets crash as one, and why even well-diversified portfolios can't escape systematic risk. And on the AI side, the first eigenvector of that 65,000-dimensional covariance matrix is the first eigenface, a ghostly average pattern that captures the largest direction of variation across all human faces. Turk and Pentland showed in 1991 that 50 to 150 eigenfaces out of tens of thousands are enough to recognize a face with 96% accuracy. Same math, two worlds. If you want to go deeper into this, watch episode 9 of The Math Behind AI. In 13 minutes, we've traveled through the entire geometry of modern finance. Correlation shapes the curvature of risk. Diversification creates the efficient frontier. A risk-free asset picks one single optimal portfolio. Beta prices every individual asset in equilibrium. And the covariance matrix that built markets also builds eigenfaces. But here's the catch. Every number in this episode assumed we knew the true covariance matrix perfectly. In reality, we estimate it from a finite sample of noisy historical returns. And small errors in the inputs become large errors in the outputs. Every slightly different estimate gives a slightly different tangency. What looked like one optimal answer turns into a cloud of possible answers. When you can't solve it, simulate it. That's next episode. This is episode 3 of our 5-part series on the math behind finance, from Brownian motion all the way to the geometry of DeFi. If this made the invisible a little more visible, subscribe to Axiom Motion and join us for the rest of the journey. Thanks for watching.